All right, everybody, let's go ahead and get started. So welcome to today's webinar on predicting and managing slope failures. We've got a panel of experts here today who have graced us with their time. And this is an interactive webinar. You'll be able to ask your questions, and I'll explain how to do all that in just a moment. But if you'll bear with me, I'm going to go through a couple of introductory slides. So today's webinar is brought to you by the Geotechnical Center of Excellence, also known as the GCE. We're housed at the School of Mining and Mineral Resources at the University of Arizona. We are an industry-funded and member-led organization, and we are quite interdisciplinary. We bring a lot of different fields of study together to conduct collaborative geotechnical research as well as education, such as the webinar that you're tuned into today. And we also pride ourselves on bridging gaps within and between academia, industry, and fields of study. Here's some photos of us having fun at the GCE. So as I mentioned, we are member funded and member led. So here's a list of our distinguished membership group. If you would like to become a member of the GCE, we would love to have that conversation with you. You can reach out to any of us individually at the GCE or email at us at gce@arizona.edu. That's probably the easiest way to get in touch with us. And so big shout out to our member organization. They are fantastic. Without their support, none of this would be possible. So today's webinar is based on two of our professional development courses. The first is Slope Performance Monitoring. These are online courses. They consist of recorded webinars from our industry experts, such as the ones joining us today. And Slope Performance Monitoring covers the topics shown in red. I won't read all of them. If you'd like to learn more, you can scan the QR code. I will also ask one of my colleagues to put a link to the Slope Performance Monitoring course website so you can learn more. And once I click off of this slide, you'll have access to that in the chat. And the Slope Performance Monitoring course was underwritten by the Large Open Pit Project, and it is based on their guidelines for slope performance monitoring book. So a big thank you to the Large Open Pit Project for their help getting the course off the ground and their continued support. This webinar is also based on our geotechnical radar monitoring course, which covers the topic shown in red there. If you'd like to learn more, you can scan the QR code, and one of my colleagues will also put a link in the chat to the radar course. So just a couple of introductions before we get started, starting with the GCE webinar team. I will be your moderator. My name is James McNabb. I'm a senior research and development engineer here at the GCE. I'm joined today by Benjamin Meyer. He is a software engineer, research and development here at the GCE. Good morning, Benjamin.
Good morning, and thank you everyone for joining us today.
And I'm also joined by Cheryl Bukowski. She is our professional development program lead. Hi, Cheryl.
Hi, everyone. Thanks for joining us.
They will be working in the background to field your questions and make sure everything is running smoothly. So a big thank you to them. Okay, now I'm going to introduce our expert panel, starting with Jeff Beal. He's a global technical advisor with Pateau Associates, and he is also a presenter in the Slope Performance Monitoring course, as well as many other courses at the GC. Hello, Jeff.
Hi, guys. Thanks very much. And looking forward to a good discussion today. This is an interesting topic.
Yeah, thank you. And thanks for joining from an airport. We really appreciate that.
No problem. I hope you like the background.
Sound fine. Next, we have Zip Zavodny. He's a senior geotechnical engineer with Zip Zavodny LLC, and he is also a senior advisor to the GCE. Hello, Zip.
Hello, everybody. Looking forward to our discussion today.
Next, we have Derek Rubis. He is a senior project manager and project engineer with BGC Engineering. He is also a presenter in the geotechnical radar monitoring and slope performance monitoring courses. Hey, Derek.
Hey, everyone. Happy to be here.
And we also have Andre Torres. He is LATAM practice lead and geotechnical advisor with Ground Probe. And he's a presenter in the geotechnical radar monitoring course. Hey, Andre.
Hey, everybody. Thank you so much for having me here.
Absolutely. Thank you all panelists for being here. Okay. Just one quick note, some background or some housekeeping rather. If you're joining today, you are muted and your video is off. So don't worry about unmuting or anything like that. It's not possible. If you'd like to ask a question, we ask that you use the Q&A function in Zoom. You'll notice that there's a chat function as well. We encourage you to use both, but keep the chat for chatting, saying hi and where you're from and so on. But if you have a specific question, if you could please use the Q&A function, that would help us out a lot. Your questions can also be anonymous if you prefer, and you can vote on questions. So if you see somebody else's question that you really like, you can give it a thumbs up and we can kind of high grade those questions. This is also a recorded webinar, and we will post it to the course sites, the slow performance monitoring and geotechnical radar monitoring courses, as well as our YouTube page, which we encourage you to follow. And maybe one of my colleagues can post a link to our YouTube page as well. We've got lots of recordings of different webinars there. And lastly, just a quick disclaimer, just note that the views and opinions expressed by our panelists are their own and do not necessarily reflect those of the GCE or any affiliated organizations. And this webinar content is intended for educational purposes only. It is not intended to be a substitute for site-specific professional advice or analysis. So thank you for bearing with me with that. And now we will get started with a kickoff discussion. So the question is, over the past decade, how has the integration of emerging technologies and analysis reshaped the landscape of slope failure management and prediction? It's quite a broad topic just to get us started and provide some background on the topic. And just to get things started, maybe I'll ask Zip to kick us off.
Sure. I think some of the key players as far as failure management, there's been a real development of TARPs over the last 10 years or so, and the ability for management to understand the TARPs and also B, follow the TARPs. That is always the critical piece. And I think this has really allowed us to get a much better handle on slope performance, potential mitigation measures to get around any type of slope failure issues, and of course also assist us in coming up with methods of slope prediction, slope failure prediction. As far as slope failure prediction, just a couple of comments, and I'll open it up for the rest of the team to talk about. Subsampling has become a major tool for us in the last 10 years or so to give us preambles of any onsetting slope failure. It has given us the ability to allow for time for failure prediction and for also methodologies for slope failure remediation, if you will. So those, in my mind, have been some of the key factors. Also, much more input coming from the subsurface monitoring systems in the last 10 years have played a major role in our ability for slope failure prediction and slope failure management. And those tools are, of course, shape arrays and other forms of subsurface data. I wish that microseismics would have become more of an important input for the subsurface data. I think microseismics will play more of a role in the upcoming few years. And those are just some off the top of my head type comments relating to this question that James put in front of us.
Yeah, thank you, Zip.
I'll just jump in. I think there's more and more operations that are mining slopes with lower and lower factors of safety. Quite a few operations I work at are mining slopes with factors of safety of below 1.3 and even down to 1.1 in some instances. And there's two things to consider when you do that. Firstly, there's the safety issue. If you're mining suboptimal slopes or slopes with low factors of safety, obviously you've got to think about the safety. And the second is the economic issue. You're obviously mining steeper, so your economics are better. But what happens if it becomes unstable and ultimately fails? So those are the two issues. And I think what the increase in instrumentation and technology has done is allowed us to adopt more of an observational approach. And so we can monitor in real time very, very small surface and subsurface deformations. And I absolutely agree with Zip on the subsurface deformations, the SAAs, TDRs, and so on. And so what that's enabled us to do is to tweak the designs as we mine them and to give us the opportunity to go into steeper, but then adjust the program as we need to. And, the monitoring systems are so good at the moment that if we follow them rigorously and follow our TARPs rigorously, we almost engineer the safety aspects out of it, because we can provide enough warnings. We've got our TARPs that safety, if done properly, is actually less of a concern. So it comes down to an economic decision of, can you mine these things steeper and get more economic benefit? And just a couple of examples I've been involved with, particularly with subsurface. I was involved with a coal mine a few years ago where they were mining one seam and had a major failure. It was a shear on the base of a coal seam, which destroyed a lot of equipment. And fortunately, there were no fatalities, but it destroyed a lot of equipment. We then put in TDRs and shape arrays into that slope, and we were able to pick up the onset of movement. And often you can pick up movement quicker in subsurface than subsurface, even with subsampling. So we're able to pick up the movement, adjust the design, and avert another failure. And that really was down to SAAs, which were tarped. So I think one thing the new instrumentations has enabled us to do is to really optimize the way we mine and manage slopes.
Great. Thank you. Andreas, you've unmuted.
Oh, sorry.
Oh.
No, you can hear me.
Yeah, we can hear you. Yeah. You want to chime in?
Yes, what I like to share with you is that I finished my studies maybe 20 years ago. And at that moment, the trend was about modeling and stability analysis, right? So we worked a lot in modeling, in susceptibility maps, and things like that. And the trending topic at that time was uncertainty, right? Everybody was working on that topic. With the monitoring data that we have nowadays, we managed to reduce the uncertainty that we have in those models, right? Now we are getting a lot of data in real time that not only allowed us to reduce the uncertainty, but also to validate the models, to provide feedback to the models that we use. So that has been great. And on the other hand, the mining industry has got very interested in these information technologies, right? Maybe the mining industry was a little bit behind of other industries in the areas of geoinformation, remote sensing, statistical analysis, and data analytics and predictive models. So nowadays, everybody is very interested on that. Now we have the data and the possibility to work on that. And I think that there is a lot of things to do now, a lot of things to work on. So I would say that that's the first. I would say that's the more important topic at this moment, right? That's the main interest now, right? Which is great to see that the mining industry is getting up to date in those technologies that has been there in the last years.
Yeah, great point. Thank you, Andre. Derek, I see you've unmuted.
Yeah, I think I'll probably just echo what some of the others have said, that an obvious benefit is that the exception and adoption of these technologies have facilitated more accurate and timely monitoring for the slopes. And what this has done is ultimately allowed us to better and more comprehensively plan and interpret slope failures. So that's already been stated, but I will also add that something we need to be vigilant about as we continue to use these technologies and as they continue to advance is that we need to avoid complacency when using them. There's always a risk of developing a set it and forget it mentality once the initial parameters are defined or as personnel turnover. And they do require frequent interaction with these systems, especially as they become more advanced and self-sustaining. Then it's easy to, again, just set them and forget them if you're so inclined. So I think it's important that these systems need to be stress tested routinely, and that can be done through vigilant observations, evaluations of the systems and the slopes, and they need to be interpreted by trained professionals. It's easy just to see an alarm on a screen and react, but to know what's going on behind that, I think is pretty important. So, yeah, and maybe one last point that in order to do this or achieve this, that the operations really need to employ and engage people who are knowledgeable about the current evolving technologies and their nuances and how they apply to their specific facility.
Yeah, thank you, Derek. Excellent points.
Yeah, the data overload, Derek, and complacency is a really important topic. There's been a couple of failures I've involved with recently. One with associated fatalities, where you go back and look at the monitoring equipment and they had enough warning, but for various reasons, the appropriate actions and TARPs weren't triggered. So one danger is that we are getting so much information that unless the operator is trained and knows what to look for and knows what to prioritize, you can get into a situation where the data overload defeats the object.
Yeah, that's a great point, Jeff.
Yeah, very good. I see that Charla Coetzee has joined us. Just to introduce her quickly, she's a group geotechnical engineer with Roytech Mining. Hi, Charla.
Hi, everyone. I'm so sorry. Was running a little bit late. My previous meeting went over.
Not a problem at all. Yeah, so I assume you can see the question here. If you'd like to chime in, we'd welcome that. If not, we can move on to the next question, whatever you'd like.
I actually want to ask a different kind of question.
Sure.
So obviously I was late. Has Zip had an opportunity to answer this question?
He has.
Okay, wonderful. I'll have to watch the recording then.
Indeed.
So just from my perspective, I think I might not answer this question directly, but one of the things I think if I look back 10 years just in my career, is where was radar? So obviously I work a lot with ground-based radars, and what was my knowledge of radar back at that point in time, or even 5 years previously. And I almost feel that with pit slope monitoring programs and managing pit slope failures, we as geotechnical engineers have been thrown into this realm of really having to understand the nuances of pretty advanced technology, which before we actually didn't have. We didn't have this kind of technology at our fingertips. So I think what I want to really say is to be kind to yourself. As a geotechnical engineer, we learned about, the principles of rock mechanics and how to log core and how to log faces. And map things and do all these different things as geotechnical engineers. But I think when a lot of us were at university, or a lot of us were in the early part of our careers, a lot of this technology wasn't available. So really understanding all these different technologies, how they work, what their advantages are, what their disadvantages are, their shortcomings, their shortfalls, the good, the bad, the ugly, is actually really, really important. So I think not quite an answer to this question, but just something to consider.
Yeah, great point.
Some of the items, sorry, Charlotte, that were mentioned and that I think are critical over the past decade is our ability to, and Jeff alluded to this, our ability to mine slopes at reduced factors of safety because of our ability to monitor well ahead of time of any type of potentially damaging slope movement. But I think the other thing that hasn't been mentioned yet, we've mentioned observational mining. Performance-based design has also kind of evolved in the last 2 or 3 years because of our ability to get this detailed monitoring data in front of us. And with this type of monitoring systems, we have become much more comfortable with our assessment of the slope and our performance of the slope. And this has allowed us to mine slopes that we probably wouldn't have mined in the past because they would have had factors of safety that are extremely low. So I think this has been a very important development over the past decade, is this observational mining and performance-based design.
Yeah, so I completely agree. I think if I go back to a publication by Peter de Brugge, and there was Luis Fernando Contreras from SRK Johannesburg. I think they published it through the South African Institute of Mining and Metallurgy, but it was the whole concept of mining with risk, and what that actually means, and then having these kind of monitoring systems to be able to go quite aggressive with designs. What I'm seeing now, there's one operation in Lesotho that SRK did a design for in basalt. I was speaking to them the other day. They actually think it's probably the most aggressive design that's ever come out of that office, but it's because there is these monitoring systems in place to be able to support that kind of mining scenario.
All right. Well, fantastic discussion, everybody. That was just the kickoff. That was amazing. So I think I'm going to go to one of our pre-submitted questions, and this actually is a good piggyback to that conversation that we were just having. So this is for the whole panel. The ability to operate beneath moving slopes using careful monitoring and forecasting has been a game changer, but I fear that continual optimization of these tenuous scenarios could lead to dangerous situations. How do we balance the pursuit of maximizing production with the increased risk of working beneath active slopes? Kind of a natural follow-on to what you guys were just talking about.
Okay, so to jump in, I think the answer to that is strict adherence to tarps. And even the most advanced mine operations sometimes fall down on their tarps. But if you're going to do that, if you're going to mine underneath unstable slopes, then tarps is totally strict adherence to tarps is something that's not negotiable. The other thing I would say is that one of the things we're seeing more and more in operations and in design is the role of rainfall, surface water, and many slopes that are potentially unstable will become a lot more unstable if it's raining. So the other advantage of the new monitoring is we're able to predict or monitor rainfall in real time. And I know a couple of operations who've actually now got Doppler radar to actually predict rainfall in advance of it occurring. So that's another consideration if you're mining underneath unstable slopes. The stability in many instances will inherently reduce in rainfall. So the answer to the question is strict adherence to the tarps.
I think that's very well said, Jeff. Strict adherence to tarps, no matter what the economic impact could be. And that adherence has to be both obviously by the geotech team, but especially by the management team. And that can be difficult at times, but needs to be strictly adhered to.
I would also say, emphasizing the adherence to the tarps, but also emphasizing what's going into their development and the robustness of their development and the analysis that's going into how those are produced gives you that level of confidence to be able to know that when you reach those levels, that's the actual point, not before, not after, but need to have all that pre-work that's done in order to define those particular thresholds.
Yeah, that's 100%, 100%, and not only the escalation of tarps, but what a lot of people sometimes forget or fail to achieve to the same standard is the de-escalation values. When is it safe to go back in there? And that, in some instances, that's as important as the tarps themselves.
I would like to say that also education is important, right? I know that the technology is good. Technology is proven technology, but in the industry there is still a lack of understanding about the limitations and the benefits of the technology, right? All the people that is participating in this course has now a better understanding of the benefits, but also the limitations. Part of our mission is to go back to the mine and make understand to the rest of the people in the mine and the rest of the operations about the limitations that the technology still have, right? We can optimize the production, of course, with the technology, but there are still some limitations that we need to be aware of, and we need to communicate to the rest of the people in the mine, right?
Yeah, I think that's such a wonderful way of explaining it, and it touched on what I kind of said in the beginning: is understanding the technology that you're using and the good, the bad, and the ugly that comes with that technology, because there are limits to radar-based monitoring. Specifically, it's the inherent physics of the system, and when developing a trigger action response plan, it's very important to make sure that those limitations are built into the trigger action response plan. And then just to touch on what Derek was saying is the period of time or re-entry period of monitoring the synthetic maps and also monitoring the trend plots for various portions of the synthetic map to see the recovery, especially of the average velocity to more nominal or background or acceptable levels before re-entry of any personnel or equipment is allowed. So there are actually some trigger action response plans that I've worked on that we've included re-entry protocols as well. And that's for a variety of different events such as blasting, inclement weather, any kind of other specific triggers or points of concern that would require the production team to be removed, and then the subsequent allowing them back into that area.
All right. Fantastic discussion. Thank you. All right. we're going to move to a little bit more of a technical question. This one is, we'll start with Andre and Charla for this one and then open up to the panel. It's about radar. And I think actually Charla may have touched on this point in her answer to the previous question. When evaluating radar data for time to failure analysis, how do you decide the number of radar data pixels to average across and the time window to average over? Good question, Jared. And I have included a figure from Graham Dick from his presentation, and where he's got, I think this is from one of his publications actually, where he's got a single pixel on the top left that he's analyzing and the corresponding charts below. And then the multiple pixels on the right, top right, and then the corresponding charts below. And then he's averaging over different time windows, just so we can get a visual of what we're actually talking about.
I think I'm going to let Andre go with this first, because this looks to be specifically ground probe data. So I'll let him comment on that, and then I'll summarize with a few additional pointers, if that's okay.
Okay, thank you. There are two things that you need to consider. Or the question has two aspects. The first one is about the average window, the time window you use. There is no a specific time window that you need to use in order to characterize a deformation process, right? In practice, what you have to do is to try different calculation periods. Could be 24 hours, 12 hours, 3 hours, 1 hour. And you have to choose the calculation period that has a better trend, that has less noise, right? So the recommendation is to have this catalog of different calculation periods, and among them, look for the one that has a better correlation. It means less noise, right? A better trend. That is going to change depending on the state of the deformation process. At the beginning of the deformation process, for example, a long calculation period could be more useful, could represent in a better way what is happening with the slope. When the failure process is increasing its speed, you will notice that the long calculation period doesn't represent very well what is happening with the slope. So you will need to change, you will need to use a shorter calculation period to get a better trend, right? And so on. That is something that you need to review all the time. Yeah, you cannot get attached to a specific calculation period. You have to change it and try to understand, to analyze, and to verify the calculation period that you are using is representing in a good way what is happening with the slope, right? And about the pixel you have to choose, of course, if you choose different pixels, you can have different forecasts, right? There is not a rule for that as well. You can try different pixels, a group of pixels, different areas. The forecast is going to vary, right? But it's going to give you a range. Could be a range of half an hour, could be a range of an hour, right? It's going to be an approximate value, right? You can expect specific forecast with specific hours and minutes to the failure, but because that is not going to happen, right? You have to be aware that you are going to have is what you are going to get is a range of time to failure, right? And that range you need to also update it. You have to analyze, reanalyze, wait for a moment. You have to compute how the deformation process is evolving, but it is going to change with the time. Sometimes the collapse is going to occur. Sometimes it's not going to happen, right? That is something that you will notice. And the best thing that you can do with this is to document the results, to recommend your observations, right? Every time you have the chance to study a collapse, right? You have to document that, right? In a database. Document the size of the failure, the specific calculation windows that you used, which was the best calculation period that provide you the best results. And in that way, you will manage to calibrate the specific time windows and the specific parameters configuration that best suits and best describes what happens with your slopes. Right?
Wonderful. Can I also add a few comments to that?
Absolutely.
So
Thank you,
I'm basically going to mirror everything that's that's just been said. I also think what's of importance is to go back to the principles. So the geology, the structure, the rock mass, the hydro. And when analyzing an area of instability is to look at what might be what we could term as being key blocks or certain portions of the instability that if that portion was to accumulate a lot more movement and to begin to fail first and is quite critical to the stability of the whole area, I would definitely be keeping a very keen eye on those portions. And then I would be looking at areas that, as Graham has done, hot spots of concentrated movement within the instability area itself, and then maybe larger portions. One thing that I do think that's important is you can have an array of different sizes of pixels or point configurations to assist with your study. But one thing you must remember is that you need to also have a combination that is representative of the alarm thresholds that you've set. So if you, for example, have selected 2 contiguous pixels or 4 contiguous pixels, make sure you have exactly that in your analysis as well, because you're then replicating alarm conditions as well. So then you know when you're going to be getting those alarms. And also, the thing with inverse velocity, it's a little bit of a black box on occasion. You need to update it literally as data's coming in every half an hour to every hour, I would say, and use a complete range of time windows, have them all plotted onto one plot, and be looking at the different range of those time windows and then what the expected predicted time to collapse would actually be. So the answer is there's no set rule. I think understanding the geology, like I said, the rock mass, the structure, if there's any hydrogeological component, and then deciding where to put these study areas onto the area of instability, and then looking at the movement accumulation profile across it as well, so that you have representative areas across the area, is probably the most important thing to do, and then updating it as often as possible. And the other thing that I've just made a note of, and I see there's also a question in the webinar chat here, is if you see that you have the systems going into phase ambiguity for certain pixels or for certain points, I think that's the point at which you would your production team should already probably have been evacuated by that point, but it's at that point that the radar's kind of reached the limitation of what it can measure interferometrically. The systems do have built-in, I'm talking on behalf of what I know, we do have inbuilt algorithmic checks to see if the system has gone into phase ambiguity, so we'd be able to tell you that. But you can also see it clear as day on the train plots as well. So if you have, for example, displacement and it's tracking in one direction, which you know to be movement towards the radar, and it suddenly flips and goes the opposite direction, that's phase ambiguity, and that's often mirrored on the average velocity trend plots as well. So I hope that helps. Derek, I think you know quite a lot about this as well. From your presentation, you touch on these kind of analysis or assessment kind of techniques and alarm assessment techniques?
Yeah, thanks, Charlotte. I would echo what's already been said. So don't need to expand on that again. But kind of going in line with some of the questions about how do you develop these if you don't have large data sets or a lot of history to lean on. I mean, there's several ways. There is the database approach, and that does require some time to accrue or acquire data. And oftentimes what sites will do is they'll review that data, they'll look at the various parameters, whether it's time windowing or area of interest, and they'll look at thresholds that would work with their current data sets. And I guess the thought process there is that anything beyond what they're seeing as background noise or baseline information, they want to know about. And but that is challenging because you do have to have a sample size to be able to run that analysis with. And the longer you're able to monitor and collect that data, the better you're able to adapt and adjust those values. They can also be seasonal as well. So if you set something up in the fall, and then you have a bunch of vegetative growth, if it's a natural slope, or if you have freshet or runoff, that can impact your baseline pretty significantly. So, so database approach is one option, and then there's the comparative approach. So, even if you don't have any information, hopefully there's case histories or other environments that are similar to what you're dealing with, and that can provide some, at least a starting point. And again, it has to be very site specific and application specific. So you need to be able to adapt those initial settings, but you can at least get a start and kind of figure out which sort of range you might want to be in for those particular thresholds.
It's already been mentioned, but I think what really needs to be stressed is understanding the failure mode. That will determine how you approach the radar-based data and how you interpret the radar-based data. So it's completely different for a brittle failure mode, let's say, or as Charla mentioned, maybe if you have a key block to look at, that's going back to Dick Goodman's approach, monitoring the passive block versus the active block. But it all kind of comes down to understanding your failure mode. That's critical in assessing and determining and evaluating your radar data.
Yeah, that's a great point, Zip, and maybe building on that a little bit, just realizing what the technology is telling you. This is radar data, for example. It's a line of sight technology, so it's telling you the distance to and from the slope. So having an appreciation for what that means. I mean, a planar failure versus a toppling failure it could look very different in terms of where it's exhibiting movement and what's actually moving. So having an appreciation for those aspects as well is important.
All right, great discussion. There's a question here, a live question that I think Derek pretty much covered, but I wanted to acknowledge it because it is a very good question, and I'll read it now. I totally agree with the comment of strict adherence to TARPs, but creating those TARP at the beginning stages without a large history of data or historic ground falls to back analyze. What approach would you use to start with the initial triggers to build the TARP? So Derek touched on this a little bit. If anybody wants to elaborate a bit more, basically, how do you get started with a TARP if you're just starting out?
Mm-hmm. I would say that.
Oh, go ahead, Andre.
Okay, thank you. I would say that the first criteria you can use, and that is something that happens a lot to us. When you go to a mine that is new to radars and they don't have any information, they don't have any database about the stability processes they have had. The best criteria that you can use is the basic one, and it's analyzing the trend of the formation process: stable, regressive, transitional, progressive. That's the basic TARP. And from there, you can work only with that, right? If you don't have any other information, you can work only with that. That is something that happens to us all the time, because we go to many places where they don't have information, as I stated before. So that's the basic, right? If you are in progressive, you are in a high risk situation. If you are in a stable, or you don't have any risk, even if you are in transitional or regressional trend, you have to be careful. So that's the basic, right? And as I said before, from there, you can start documenting your observations, right, in a structured way. And you can start to calibrate those thresholds that you need for your TARP, right?
Yeah, and let's not forget site inspections, particularly in the early phases of a project. I mean, I think, again, to build on the discussion that a lot of slopes are being optimized, we're ending up with fairly steep bench face angles, and sometimes double, sometimes triple benches. And the potential for falls of ground and rockfall increases, and monitoring systems at present, yeah, they'll pick that up, but they may not give us enough warning. So let's not forget the site inspections, and those site inspections are definitely applicable when you don't understand the site in an early phase of a project.
I
think-
would also. Oh, go ahead.
Oh, sorry, you go first, Derek.
Oh, thanks, Charlie. I was also going to say, maybe it's more of a caution as you are looking at options for developing these TARPs and then implementing them. What we typically recommend is that you implement them initially in a very isolated environment where the folks who are directly involved with operation and monitoring using those units are getting alarms. You'll probably get a lot of pressure to have those alarms go out site-wide early on. But if you are learning your slope and you're evaluating the reactivity of the system to the TARPs that you've defined, it's often nice to be able to do that in a little bit more of an isolated and controlled environment. So, it's not going out to the entire mine site, and you're not, canceling or moving people out of certain areas preliminarily or too early. So that can have the adverse effect of kind of the cry wolf mentality, where if you're learning your system and you're implementing it and all these alarms are going out, then people lose confidence in the system. So just having an allowance for that learning process for how your slopes are behaving and how they're showing up on these systems, I think, is important.
Lovely, Derek. Thank you. I've just made some notes to add to what's already been said. And what I normally tell our clients is, when we commission a radar system, it's not just about physically building the system and giving the team on site training and then leaving you to kind of just get on with it. Commissioning a system takes a number of months, in the sense that you need to set up those scan regions, analyze the data, and understand what the data is actually telling you, which then feeds back into the trigger action response plans. And it's quite important to explain to management that commissioning isn't just about physically putting the system down. It's about understanding, like I said, and then utilizing that data. That's part of the commissioning process. So the first thing is, the service providers know the drill. We've and the consultants as well. We've seen quite a lot. We would have experienced quite a few sites, so we have a pretty good idea of where you should be beginning, and we can give you advice on that if you actually want us to, and to be able to look at your data and just give you an idea of where to start. And I think when you are testing these different combinations in the beginning, or beginning to analyze your data and to put alarm thresholds on, Don't try and do too much in one go because it can become really, really chaotic. Just going back to what Derek has said, just be really careful with that. And personally, I would keep the critical evacuation alarms off for a period of time until you actually 100% understand that when those kind of alarms go off, they are really meaningful so that you don't create any kind of complacency. Hand in hand with that, the database kind of approach and periodic reviews. And the other thing that could be really useful is you might have brother or sister mines close by working in very, very similar geotechnical environments. They might not have the same system, so maybe they don't have like a RA or a SAR or a direct way of comparing the monitoring method, but they will probably have a good idea of what Andre was saying. What is a kind of nominal behavior? What's progressive behavior? You know, what do those trend plots kind of look like? And if they're willing to share, you know, just some of their advice and their learnings on what they discovered when they've been monitoring. It's quite useful to do that if you are able to set up those kind of meetings and just have those discussions with nearby operations.
It's very well said, Charla, is once again understanding the geology and making use of nearby or similar geology. It can be very helpful in developing these early tarps. But one thing I don't think we have mentioned today is that all of these tarps really require periodic revisions as you gain additional data. And those revisions really should be accepted. They need to obviously be done very professionally and reviewed by the entire team, including management. But tarps are not permanent, if you will. They require modifications as you get more data.
I would like to add also that now that INSAR has become so popular, that is something that has helped us in a number of cases in order to have a general view of the risk levels in different areas of the mine in advance before placing a radar, right? Before placing the radar, we can identify this area is already having a deformation process. This is becoming progressive, and so on, right? We all know that INSAR has limitations regarding, is not real-time monitoring and has limitation on detecting things that are moving faster. But you can have an initial zonification of the risk levels in a pit and in different areas of the pit based on that data, right? So it's becoming very, very useful when you are planning the deployment of a radar and when you are planning how to use the radar in the mine.
Right. Fantastic discussion there, and thank you for the live question. Looks like we have about 6 minutes left. I'm going to go to one more question, and I think it will probably take up the rest of the time. It's a fairly broad topic, and it's more like 2 questions. What does slope failure management look like? I imagine there's going to be lots of different responses for that. And then second part, if slope failure is imminent, are there ways to help it along? In other words, get it over with. It's kind of 2 different questions, but you can take your pick or both.
Just a very quick comment on the second half of this question. Whenever I've tried to bring a slope down, it has never worked. We tried blasting down some of these slopes. Actually, the initial Kimberley pit study, which is the work that was done in the 60s, and that was the original U.S. Bureau of Mines effort. The final piece of that was to make the slope fail. This is in the Liberty Pit at Nevada. And so we blasted the toe, and we were very confident that the thing was going to come down, and it never did. And I've tried that in a number of other places. I've never been able to bring down a slope that I wanted to bring down.
Zip, would you say? Sorry, I just want to ask Zip a question. Sorry, Jeff. Zip, would you say the more you fiddle, the less you know? Because you've changed everything.
Yes, Charlotte, I think the more I play with slopes, the less I know about them. I agree with you.
And then, the more you try and like you said, you try and blast a portion or take a portion down, you're changing the parameters of it completely. So kind of changes the behavior per se.
Yes.
So I think that most people who've done it, and I've been involved in lots of issues on this, is that you tend to make it worse. So it never goes the way you think it's going to go, and you very, very frequently end up with a situation which is worse than before you started. The one exception, though, is isolated rocks, big blocks, which can be brought down by various mechanisms. So if we're looking at the small tonnages, small falls of ground, isolated rocks, those can be brought down. And I think we've all been in there when we've gone up, sent people on ropes and whatever to blast an overhang or to bring down a small fall of ground. So that's there's a lot of experience on that. But larger scale slope failures, my experience is you often end up, well, always in my experience, I think you end up with a worse situation than you started.
All right. Well, very, very interesting indeed. Any thoughts on this first part? What does slope failure management look like? It's a very, very broad question. I imagine there's lots of different answers to it. We have 2 minutes to cover it.
Okay, I'll give it 30 seconds.
Okay. Good.
What does slope failure management look like? It's exhausting. It's very time consuming. There's a lot of emotion that goes into it. A lot of frayed tempers. Everyone's obviously heavily invested in making sure everything is safe. So people do need to take breaks and to have a timeout. And I think the most important part of slope failure management is personnel management and making sure the team, that certain things are handed over to different members of the team in times that everyone can kind of share the distribution or the load of actually managing that instability. And that you sit down and have regular discussions about everything and keep up to date and appraised of exactly what's going on. That's what I'll say about slope failure management.
Yeah, and I guess to bring the conversation around full circle for an hour ago is that there are lots of people that are mining failed slopes, and again, it's the strict tarps, strict monitoring, and making sure you have enough time to pull people and equipment out. But there are lots of people mining failed slopes.
All right. Well, that brought us to time. I hate to cut it short. I know we could probably talk about that question for a long time. Just before we go, one quick plug for our professional development program. Here are our courses that we offer. So this webinar was based on the geotechnical radar monitoring course in red here and the slope performance monitoring course. We just released this year our fundamentals of open pit slope design. That one is fully released now. We're signing, we're registering for the 2025 iteration of that course, and upcoming in September will be our newest course, blasting in pit slope performance. So be on the lookout for that. You can always go to our website, GC at Arizona. Well, why don't one of my colleagues put that in the chat? I don't recall what it is exactly. But if you Google us, GC, University of Arizona, you can find it there. And so with that, I will give a big thank you to our panelists and everybody that participated today. It's a wonderful discussion. Sorry we couldn't get to all the questions, but that's just how these go. And yeah, so thank you for your time.
Thanks, everyone. Great discussion.
Bye, everybody.
Thanks, everyone.
Thanks,
to everybody.
guys. Yeah. All right. Thank you. See you later.
Bye.
Okay. Safe
Bye.
travels, Jeff.
Bye-bye.
All right. On a bus now. So there you go. See ya.
Okay, take care.
Bye-bye.